Hello, everyone. Welcome back to everyone at COP26 and at our hubs and also watching online. I'm thrilled to present Dr. Libby Jewett, who's going to talk to us about polar acidification. Thank you.
Thank you very much. Glad to be here at the COP26. My name is Libby Jewett. I am director of NOAA's Ocean Acidification Program. And today we will be talking about polar acidification deep dive, in which we'll be looking at both the Arctic and the Southern Ocean. But first, next slide. I have a few slides myself. Oh, yes. Here we go. Here we are. Beautiful logo, the NOAA Ocean Acidification Program. So just to set the scene for the lineup of speakers that we will have, wanted to make sure that we all remember what ocean acidification is, which is as CO2 goes into the atmosphere, part of it stays in the atmosphere, part of it's taken up on land, and about 26% or so is taken up by the ocean. And it's because of that, the ocean taking up the CO2, that it causes the acidification of the ocean. And I'm not going to go into all the chemistry of that. Maybe some of our speakers will be doing that. But just to give you a quick summary, this is data that's been collected at the Hawaii Ocean Time Series for many years now. And the top red is the measurement of CO2 gas in the air. The blue right below that is the CO2 that has been taken up by the ocean, obviously tracking quite closely, as any gas that's in the air will be taken up by the ocean. And the follow-on change that is happening as a result of it taking up the CO2 is that the pH is decreasing, which is the black line, and the carbonate ion concentration is also decreasing. These are the reasons that we are very concerned about ocean acidification, and you'll be hearing more about that from our other speakers. Now, this is a graphic taken from the IPCC Special Report on Oceans and Cryosphere, in which we're showing the difference between if we overshoot in terms of high emissions, or we are actually able to meet our commitments in the Paris Treaty. The difference in the effect on our polar oceans is quite dramatic. As you can guess, red is not good. Red means that the polar ocean is dropping below a healthy saturation state. And so we need to, this is just quick to remember. This is why why we're here at the Conference of the Parties. The other is to note that the rate of ocean acidification and actually the rate of CO2 emissions is 10 times higher than has happened in Earth's history. And the comparison here, the big black bleep there is how much CO2 is being emitted now and how short a time it's being emitted within, compared to the last large emission of CO2, which happened about 55 million years ago, over a hugely longer time frame. And we know from documentation in the paleo record that long, CO2 emissions that were extended over millions of years also had negative effects and made a lot of changes in the ocean and biota. So obviously, if something is happening 10 times faster, we need to be concerned. And again, looking at the low carbon future versus high carbon future, looking at the pH change that we are predicting through ocean models, and our first speaker will actually be also talking specifically about modeling OA parameters in the Arctic. you can see that the recovery from a world in which we don't reduce emissions is much longer. And in fact, we probably won't ever reach back to the way it was pre-industrial, according to our modeling. So another reason why we really, really have to meet our carbon targets, if not up them. And so finally, we already are seeing negative effects of ocean acidification on biota, and we will be hearing about fisheries impacts in the ocean. Here you can actually see a very tiny swimming snail called the pteropod, and that has been corroded by ocean acidification, acidified waters in situ. So these are not experiments. This is actually specimens that are collected in parts of our ocean that are more acidic than other parts of the ocean, and already we're seeing impacts. So for all these reasons, we have to focus our attention on collectively making a difference and making sure that the future for our oceans is a good one. So our first speaker, now we were going to have a series of speakers covering modeling and impacts and ecosystems and Southern Ocean. And we're very excited to have our first speaker, who is Dr. Nadja Steiner, who's a senior scientist with the Departments of Fisheries and Oceans and Environment and Climate Change in Canada. She develops and analyzes coupled ocean ice ecosystem models for Arctic marine ecosystems, with a special focus on understanding the drivers of change, such as ocean acidification.
Welcome to the COP26 Cryosphere session on polar acidification. My name is Nadja Steiner. I'm a research scientist with the Departments of Fisheries and Oceans and Environment and Climate Change in Canada. Earth system models are our only way to project climate change into the future. Here I would like to present model projections of Arctic ocean acidification to convey the following key messages. Ocean acidification caused by the continuous uptake of CO2 is faster paced and more advanced in the Arctic. There is significant regional variability in the Arctic. Models show consistent trends and increased certainty in Arctic ocean acidification over time. Ocean acidification until 2023 is already defined by past emissions. After that, higher emission scenarios show faster acidification. For regions with most advanced acidification, aragonite undersaturation will be reached in all scenarios. For other regions, lower emissions can still avoid undersaturation. These environmental changes have impacts on ecosystems and Arctic communities. In 2021, several assessment reports have been published. I would like to focus here on the IPCC 6th Assessment Report and on the Arctic Monitoring and Assessment Program Arctic Climate Change Update. Both reports highlight that the physical drivers of Arctic change continue to change rapidly, including rapid warming and ocean acidification, and these changes are driving rapid transformational changes in Arctic ecosystems and major impacts on Arctic communities. The figures we're seeing here are from the IPCC report and show results from the coupled model intercomparison project CMAP6 for temperature, Arctic sea ice, and pH, a measure of acidity. The temperature is increasing rapidly for 5 different emission scenarios. It shows higher increases for higher emissions and lower increases for lower emission scenarios. Arctic sea ice melting also shows differences among the emission scenarios, with higher emission driving a faster reduction in Arctic sea ice. For ocean acidification, in this bottom figure, we see that a higher emission scenario leads to a faster decrease in pH and hence a faster increase in ocean acidification. I would like to highlight here that impacts of reduced emissions only start to show after the year 2035. In the Arctic, ocean acidification has progressed faster than in any other ocean. However, there are regional differences in the Arctic. On this slide, we are seeing CMIP6 model results showing the mean of 9 Earth system models for the highest emission scenarios. And we're looking at regional differences for the calcium carbonate saturation state omega. The calcium carbonate saturation state is defined for two forms, aragonite and calcite, which are the two forms produced by marine organisms to form their skeletons. If the calcium carbonate saturation state goes below 1, then these skeletons start to dissolve. What we are seeing here is the range of regions as shown here. We've distributed the Arctic into multiple regions, and we are seeing highest ocean acidification and most progressed undersaturation for the East Siberian Sea, which is this one, and the highest saturation states for the North Atlantic influenced Nordic and Barents Seas. For calcite, which is dissolved later than aragonite, the saturation state is still higher, around 2.5 for the mean of the models, but will also lead to undersaturation by 2080. In this slide, we are looking at 9 different Earth system models from the CMIP6 suite, and we are looking at calcium carbonate saturation state omega aragonite for the high emission scenario, SSP 585, and the top 60 meter in the ocean. We are looking at 3 different regions, the North Beaufort Sea, East Siberian Sea, and the Barents Sea. What we're seeing is that Earth system models show fairly consistent trends, but biases among the models. For saturation states, these biases decrease over time. Uncertainty in the initial or earlier time is partially related to limited observational constraints in the carbon system, but also to the varying pace in sea ice retreat among the models. For the different regions, we see that for the East Siberian, with an advanced ocean acidification, aragonite undersaturation is already reached to current times for most of the models. For the Barents Sea, we see still supersaturation at current times. On the other hand, we're seeing the temperature for Beaufort Sea in this bottom panel would increase over time, and we see that the bias among the models increases over time due to the higher variability in regions with open water. Here we are zooming into 2 regions, the North Beaufort Sea and the Barents Sea. And we are looking again at aragonite saturation state, this time for 2 different emission scenarios, 585 and 245. What we are seeing is that ocean acidification until about 2035 is already defined by past emissions, after which higher emission scenarios show faster acidification progression than the lower emission scenarios. For regions with most advanced acidification, which is, for example, the North Beaufort Sea, aragonite undersaturation will be reached in all scenarios. For other regions, like the Barents Sea, lower emissions can avoid undersaturation before 2100. This slide summarizes the results in form of heat maps, where colors indicate the number of models crossing a certain threshold. Thresholds are for omega aragonite, a saturation state of smaller than 1, for temperature 5 degrees, and for summer ice concentration 15%, which we regard as open water. On the y-axis, we see the different regions. On the x-axis, the time. And the models show a range of timing for thresholds crossings, as we can see here, but consistent regional differences. So like if it starts later, it starts late for all the models. We also see a consistent pattern between the temperature and the summer ice concentration. In summary, ocean acidification is faster paced and more advanced in the Arctic. There is significant regional variability in the Arctic and consistent among models. Models show consistent trends, but biases among models. For saturation states, the biases and uncertainty decrease over time with decreasing sea ice, and the initial bias might also be related to limited observational constraints. Emission scenarios show consistent ocean acidification until 2035. Afterwards, the higher emission scenarios lead to a faster ocean acidification. For regions with most advanced acidification, aragonite undersaturation will be reached in all scenarios. For other regions, lower emissions can avoid undersaturation. For the highest emission scenario, All Arctic regions show aragonite undersaturation by 2080 and calcite undersaturation for all but 2 regions by 2100. These environmental changes drive impacts on ecosystems, nature's contribution to people, and good quality of life for Arctic communities.
Before I introduce our next speaker, for those of you in our audience, especially our live audience in the broader world, you can tweet us questions or comments if you use the hashtag COP26 polar_OA. That's hashtag COP26 polar_OA. And we have someone who's going to be managing our Twitter feed, and your questions are going to come to our speakers are all going to be live here. Well, not live here, but live on the screen at the end of this event and can answer your questions. So without further ado, we have Dr. Helen Findley, who is a biological oceanographer at the Plymouth Marine Lab here in the UK. She uses a combination of experimental, observational, and modeling tools to investigate impacts of climate change and OA on marine life with a special focus on the Arctic. She is also co-chair of the Northeast Atlantic Hub of the Global OA Observing Network, which we will be hearing more about with our last speaker. So take it away.
Thank you, Libby, and thank you for allowing me to speak to you today. So I'm going to be talking to you more about the biological impacts. I'm hoping to give you a general overview of how ocean acidification has the potential to impact organisms and species and what that means for communities in the polar regions. So we've heard about how ocean acidification is manifesting in terms of the carbonate chemistry changes and what those model projections are looking like in the future. But why do we expect that to be a problem for organisms? Well, just like humans, all organisms have to have a stable internal pH. They need to maintain their internal physiology to allow biological processes to function. So there can be direct impacts on those organisms. If you are living in a marine environment where that pH is changing, then you have the consequences is that you might not be able to buffer those changes in pH. And so that could have impacts on your physiology, or impacts on growth, impacts on reproduction, behavior, and health. We heard a lot about calcium carbonate saturation state. So for many organisms, they need to calcify. They produce calcium carbonate shells or skeletons, things like cockles, mussels, oysters, corals. And these have the addition of having that energetic process of having to calcify. And especially if we think about in terms of living in a potentially more corrosive environment, if they have structures that they're either directly exposed to that, then they're going to be dissolving. But even if they need to, if they have a cover encasing those skeletons and shells, then they will actually still potentially expend more energy to try and balance that internal pH, which allows them to do that calcification process. So there's an energetic trade-off quite often when we see changes in the ocean pH that impacts these organisms. But you can also experience indirect effects, and I'll talk about some of those in more detail in a minute. But if we think about the potential change to food web structure, to predator-prey interactions, and to competition. So this just highlights again the fact that calcifiers, this is an example here of mussel shells that have been put in different ocean acidification conditions. This is from an experiment, just showing how that dissolution might look. And you can imagine if these organisms are being exposed in the real world to these undersaturated conditions, it's maybe not something you want to have on your dinner plate, is this appearance. So even the appearance of these organisms and their internal structures can actually have a consequence for how we as humans think about these organisms and value these organisms. And that's important to consider as well as the actual biological consequences. But we're already on a trajectory down to kind of pH 7.7, potentially as a global average. And that means that we're kind of considering these organisms that are going to be potentially showing quite severe conditions to the dissolution of their shells. But animals are not just these lumps of chalk. They're not just these exposed calcium carbonate minerals. And this energetic balance that they can shift energy around within their biology to actually overcome some of these issues, overcome some of this corrosion, especially if there is extra energy available within the food system. But quite often what we see is maybe that an organism will have a thicker shell, it'll be able to still calcify, but actually that maybe comes at a cost. So perhaps it doesn't grow as well, or it doesn't have such good reproduction. So just to highlight where we are in terms of knowledge for the polar oceans and ocean acidification, this was the AMAP report, came out in 2018, the Arctic Ocean Acidification Report. And there were over 186 studies that were talked about in this report. 74 of those were from Arctic or subarctic species. So there's a real lack of understanding of what's going on with proper Arctic and polar species. So a lot of the information that we have on how organisms will respond to future ocean acidification comes from lower latitude species. And that is a problem because we know that the Arctic environmental conditions are already very different to elsewhere. And there may be ways that these species are already pre-adapted to conditions, or they may be more or less sensitive to the similar populations, but further south. And so we really need to enhance our ability to go up and study those Arctic or polar specific species. But what we do know is that there's a large heterogeneity in responses. So some species are responding positively, others are not. And we really need to understand the mechanisms to improve our predictions. But we can kind of get a general sense of what's going on. We know that early life stages tend to be more vulnerable. They have less ability to buffer these changes internally in their physiology. Exposed calcified structures are more at risk. And that's evident in some of the responses that we're seeing in some of these calcified organisms. And endemic species and those of restricted geographies are also potentially at risk because of local changes and local conditions that manifest and exacerbate the global ocean acidification problem. But we are observing change today in the oceans as we know them in their conditions. So we do know that in terms of the chemistry, there are hotspots. And we saw from Nadja's presentation that, for example, in the East Siberian Sea and along some of these areas in the Arctic, that we're already experiencing undersaturated or corrosive conditions and low pH conditions. And as Libby highlighted, the pteropod story is one that's been a kind of symbol of ocean acidification. So this is an example from Nina Bednasek's work, where she's been looking at pteropod shell dissolution in a number of different places, in the polar oceans, in the Arctic and the Southern Ocean, but also in hotspots around Canada. And what we find is that if you increase the saturation state, then you get less dissolution, and you can actually see that in the areas where there is more corrosive waters, then you're getting more of this dissolution. The same's been found now for larval crab exoskeletons. So this is the Dungeness crab off the coast of Alaska. And the larval stages here are sexually vulnerable to dissolution and even damage to some of their sensory organs. And we're also seeing some reduced calcification rates in the Southern Ocean, and they relate to things like calcifying phytoplankton species, coccolithophores. So that's the direct impacts. Some of the indirect impacts we know from laboratory experiments. It's very difficult to actually measure indirect impacts in the field, so we have to return to the laboratory to explore those. And we can think about changes in food quality as one example. So if we expose phytoplankton, in this instance, up in the far left-hand corner, to different levels of pH or CO2, then they actually change their nutrient status, the amount of carbon-nutrient balance that they have within them. If you feed that phytoplankton to their grazers, the copepods, then that actually contributes to a change in the production rate and the development rate, respiration rate of these organisms. So there's a knock-on consequence, not only from the direct impacts of low pH and high CO2, but actually of that transfer of organic nutrient and food quality for these herbivores. We also know that there's predator-prey interactions that could potentially be affected. There's been work done on fish species and also some crustacean species, where we've been able to manipulate the conditions so that you can expose these creatures to a predator queue and measure how much time they spend in that queue. Over on the left, we've got an example from clownfish where they're exposed to a predator queue, and they spend about 10% of their time in that queue, and the rest of the time they're hiding away from the predators. But if you expose them to lower pH conditions, they spend much more time in that area. Up to 60% of the time is then spent in the predator queue. So they're not able to detect that predator queue as well. And the same has been found for pink salmon, which is very relevant for the Arctic and the subpolar regions. So again, we can see that as you increase the pH, lower the pH, increase the CO2, then you're seeing a decrease in predator avoidance and decrease in predator detection. We also know that natural variability can impact organism behavior, and we can kind of learn from what the organisms are actually experiencing and think about how they might respond to future oceanification. So this is work from a couple of years ago now, but it highlights in the Arctic Ocean, if we think about species and what they're doing, they're not just stationary species, they're actually experiencing a very variable environment potentially. So this is an example of 2 copepod species. The Calanus species is a larger species, and it has a vertical migration, if you see in this panel D, going from about the surface down to about 200 meters in the Arctic at certain times of the year, compared to the Oceana, which is a smaller species and has a much narrower vertical distribution at certain times of the year, which is also comparable to the Nauplii, which is the larval stages of the adults. You can see from panel B and panel C that the pH and the CO2 levels are actually varying across that depth range as well. So those organisms are naturally going across quite a variable level of pH and CO2. And if you then take those organisms and expose them to laboratory conditions, you actually see that the adults, the ones that are migrating across that range, have very little impact in terms of ocean acidification. But the smaller ones, the Oceana and also the larvae, the Nauplii stages, have decreased survival when you expose them to higher conditions. So we can learn that organisms that are able to kind of have this pre-exposure to ocean acidification may actually have mechanisms to cope with that compared to organisms that perhaps don't experience such a variable range. So those impacts on individuals, but also on their interactions, manifests itself to impact on the food web. We can see that there's likely to be increased primary production in the Arctic, primarily as a result of the opening of the Arctic, the ice-free regions, which allow further light to come in, but also changes in nutrient dynamics will impact that. And CO2 actually benefits a lot of phytoplankton species because they are actually taking it up. It's almost a nutrient for them. So we may see increased primary production, but what we're likely also to see from experiments is a shift in the size structure. So that could result in much smaller species being present, and that has knock-on consequences for the rest of the food chain. We've seen examples of where we have changes in key secondary consumers, either directly through this shell dissolution or impacts on their physiology, but also through this change in nutrient dynamics as you go from the food that these grazers are eating and the quality of that food that they're going to be consuming. That quality of food is passed up along the food chain. We know that there's likely to be changes in size of organisms and their nutritional status. So again, the nutritional status of these herbivores and the oysters, the clams, the mussels, the things that we're interested in consuming, as well as shell fisheries, as well as being food for organisms, that is likely to change as a result of these worst case ocean acidification scenarios. And again, we can move up to the kind of higher level food level, where we're looking at direct impacts on maybe early life stages of some of the higher predators, the higher fish species, but also thinking about these predator-prey interactions. So although we don't know everything about what's going to happen to biology and the ecosystems in these remote environments, we know a significant amount to be concerned, and we know a significant amount that will allow us to make some projections about how we should be looking at this. And if you think of a risk analysis, we know the hazard is there, we know the level of exposure, we maybe don't know the sensitivity of everything, but if we can minimize that exposure, then we don't have to worry quite so much about how sensitive everything is, because they're just not going to be exposed to it. So I'd like to just end by reminding us that we don't have to go on this worst case scenario, these high emission scenarios. There are ways we can mitigate that. We can minimize the impacts of all of these aspects. These are generally, in lab experiments, we tend to use these kind of high CO2 levels. So all of this will be minimized if we reduce emissions. But we can also manage co-stressors, as I pointed to and alluded to earlier. There's many other things going on that will also impact these biological processes. If we can manage those co-stressors, then we can also help to mitigate the impacts on ocean acidification. We can protect and increase habitat, then that will help to help mitigate against this issue. And again, investing in science partnerships and educations will allow us to provide the evidence and facilitate that knowledge exchange between policymakers and stakeholders. Thank you.
Thank you, Helen. And I think your last slide is very powerful, and you're going to be hearing those same refrains from our other speakers. Now, if you want to talk to us and ask us questions from out in the live audience, hashtag COP26 polar_OA. And we're gonna ask those questions to our panelists at the end of our session. So our next speaker is Dr. Thomas Hurst, who is a research fisheries biologist and program manager for the Alaska Fisheries Science Center at the same agency that I work at in the US called NOAA. Tom's research blends field studies and lab work to examine the environmental ecology of early life stages of marine life, notably Arctic fish. Take it away, Tom.
Hello, everyone. I am Thomas Hurst, research fish biologist with the U.S. National Marine Fisheries Services Alaska Fisheries Science Center. I want to thank the organizers of the Cryosphere Pavilion and today's session on polar oceans for the invitation to provide this overview of the impacts of ocean acidification on Arctic fisheries. By now, you are well aware of the phenomenon of ocean acidification. Nadja Steiner gave an excellent overview discussing some of the unique aspects of acidification in the Arctic and how acidification is expected to progress in different Arctic basins. We also know that ocean acidification is not acting alone. The CO2 increases in the atmosphere and the associated warming and loss of sea ice are occurring throughout the polar seas. In this talk, I'm going to focus on the risks and impact of ocean acidification on Arctic fisheries and the people that rely on Arctic marine resources for nutrition and culture, as well as to fuel their economy. I will primarily use examples from the Bering Sea and Alaskan Arctic, as that is where my work is focused, but similar examples can be found throughout the Arctic basins. Over the past decade, research on the impacts of ocean acidification on marine species and ecosystems has expanded rapidly, with the previous presentation by Helen Findley providing an overview of some of those impacts. Here I show an example of experimental work on the OA effects on juvenile red king crab. Researchers held crab in the laboratory for over 6 months under ambient and reduced pH conditions. They found a clear effect of acidification, with crabs at low pH having significantly higher mortality rates than crabs at ambient conditions. In addition, the crabs at low pH grew more slowly, took longer to molt, and had smaller increases in size during each molt. Those laboratory observations of CO2 sensitivity were then incorporated into a model of impacts to the fishery in Bristol Bay region of the Bering Sea. The trajectory of yield in the fishery over the next 100 years was sensitive to how the survival patterns observed in the lab were applied in the model, but in both cases of the model, there was a 95% reduction in the fishery harvests by the end of the century. Effects such as those just described are not limited to shellfish, as OA sensitivity has been observed in a range of commercially and economically important fin fishes as well. These dynamics are being explored throughout the Arctic Ocean, as reviewed in a recent report from the Arctic Marine Assessment Program. It can be easy to overlook the magnitude of some of the major fisheries in the Arctic because they are distant from the major population centers of the world. But Arctic fisheries contribute to the worldwide market for seafood and represent major regional industries driving local economies. In the United States Bering Sea alone, fisheries for crab, fish, and scallops produce approximately 2 million tons of food annually, with first point of sale, or what is known as ex-vessel value, of about $1 billion per year. The greater Bering Sea fishing industry supports the equivalent of approximately 15,000 full-time workers, with much higher numbers of individuals participating in some component of the fisheries economy. The commercial fisheries in the Bering Sea drive the economy of local communities, but the seafood that is harvested is distributed throughout the world, so the changes in Arctic ecosystems and Arctic fisheries will be felt in markets and by consumers across the globe. While acidification will have significant impacts for some of the world's major high-latitude fisheries, it will also impose much more immediate risks for people who rely on subsistence harvests to meet their basic nutritional requirements. In 2014, the Alaska Department of Fish and Game surveyed Alaska communities to evaluate rates of wild food harvests. As you might expect, subsistence harvests were low in the larger municipal areas of Anchorage and Juneau, but it was significant in rural communities of Alaska, and as indicated in the red bars in this figure, subsistence harvest was highest in the communities along the Bering Sea coastline and in the Arctic. In addition, when we include sea-run salmon along with other fishes, marine mammals, and shellfish, we see that about 70% of the wild foods harvested by Alaskans come from the ocean. The high levels of subsistence harvest of marine resources means that these Arctic communities are especially vulnerable to food web disruptions that could come about from acidification or other aspects of climate change. Now, getting back to why everyone came to Glasgow for COP26, it is critical to note that we can still do something to constrain the impacts of our ocean acidification. On the left is the well-known projections of atmospheric CO2s associated with the different RCP pathways. The figure on the right shows the trajectory of aragonite saturation states in the surface waters of the Bering Sea shelf. This is where the larval crab that I mentioned earlier live, along with larval Pacific cod that I study, and pteropods that are the food for many marine resources. As discussed earlier, there's a lag between CO2 emissions into the atmosphere and those effects being seen in the oceans. The pathway of acidification in the Bering Sea is essentially set until about the year 2035, based on the continued absorption of CO2 that is already in the atmosphere. However, the severity of ocean acidification after 2035 depends on the decisions and actions that we take as a society about CO2 emissions today. As a final point, I'd like to bring the focus back to the people and communities that are going to be affected by ocean acidification and other aspects of climate change. When we hear the phrase Arctic community, we may immediately think of a place like Gamble, Alaska, on St. Lawrence Island in the Bering Sea. Gamble has a population under 700 people, over 95% of whom are indigenous Native Alaskans. The community has a tribally centered governance as a native village. And while there's relatively little commercial fisheries harvested in Gamble, the people rely heavily on subsistence harvest of marine mammals along with a range of fish species. In addition to meeting the direct nutritional needs of the community, these subsistence harvests are critical to the cultural traditions of the community and support the local sharing economy. In contrast, places like Unalaska or Dutch Harbor represent a very different type of Arctic community. On the southern edge of the Bering Sea, this community is a major international fishing port with substantial industrial infrastructure supporting regional fisheries, including seafood processing facilities and international terminals. More seafood is landed in Unalaska than in any other port in the United States. And in between these extremes is St. Paul, a third island community in the Bering Sea. With over 80% of the permanent population identifying as Native Alaskan, it also supports a large migrant community associated with seasonal fishing industries. As in Gamble, subsistence harvests of seals and other marine mammals are important to the people of the community, but the commercial fishing industries for crab and halibut are also a major economic driver. Ultimately, it's important to remember that the impacts of acidification and climate change will be felt very differently across the communities of the Arctic. So summarizing the issues facing Arctic fisheries and communities, our understanding of ocean acidification has made great progress in the last decade. However, there is still a lot we don't know. We have to maintain focus on resolving questions about the chemistry of ocean acidification, as well as the biological, ecological, economic, and sociological impacts of acidification. When we discuss the impacts of acidification, we have to remember the diversity of Arctic communities that are being impacted and recognize the distinct risks that each faces. Some are major industrial fishing ports that export food across the globe. Others are remote, isolated communities of indigenous peoples who rely upon the local harvest of marine resources as a primary source of nutrition, which is inextricably linked to the identity and culture of the community. Models tell us that recovery from climate-induced changes in ecosystems will take a long time. And unfortunately, we need to acknowledge that the risks that some things that could be lost may never be recovered. As warming occurs, some species will move north into newly available habitats, but for Arctic species, there may be nowhere to go. If a species or a genetically distinct population loses their last refuges due to warming or acidification, they'll be gone forever. And in a similar way, we know that the lack of access to natural resources can disrupt the transfer of knowledge about traditional harvest practices and deprive peoples of their cultural heritage. Finally, oceanographic forecast models tell us that the near-term trends in acidification are already set in motion. This makes it ever more important to act now to avoid the more severe consequences going into the future. If we want to avoid the most dramatic consequences of warming, sea ice loss, and acidification, we must take the necessary steps to act as soon as possible. Thank you for your attention.
So our next speaker, well, before I give you our next speaker, remember, live audience, that if you would like to ask questions or provide your comments, use Twitter, hashtag COP26polar_OA. We're waiting. We're waiting for your questions and comments. So our next speaker is Dr. Richard Bellerby, who is here in the audience, is lead researcher at the Norwegian Institute for Water Research and also director of the Center for Marine and Coastal Research at East China Normal University. He researches the interplay between climate and ocean change, marine ecosystems, and ecosystem services, including socioecology.
Right, thank you for the invitation and this opportunity to give some empirical support to many of the discussions and evidences shown earlier in earlier talks. I'm going to focus on recent observations or publications which have been made since the last AMAP ocean acidification report and try and show a pan-Arctic view of how the system is changing. Something that should bear in mind in the Arctic or in any region which has a very strong land-ocean connection that is very different. We've seen evidence from Libby of the open ocean time series at Bermuda and Hawaii. Those are preliminarily driven by anthropogenic carbon uptake, and that's the pure definition, the original definition of ocean acidification. But in the Arctic, we have other contributors. Some of them can be even greater than the anthropogenic carbon. We have massively increasing concentrations of organic carbon coming in from Arctic rivers due to permafrost melting and erosion and transfer through the rivers. We also have very rapid freshening, again, through the increase in precipitation and input from rivers, but also through the very rapidly thinning sea ice cover. We also have very local effects, potentially very large effects from methane release and the potential of that oxidation within the water column. So there are many different, it's a much more complex system to understand and to observe. But we should be heartened. And when we did the first AMAP acidification report in 2013, there were very, very few measurements. 2018, we have more, and I will show you now that one, that we have more measurements, but our time series are extending, giving us much more confidence in supporting the modeling work that has been shown, giving a basis for the experimental work and actually supporting what, I mean, Helen said, the very high CO2 concentrations that have been used in the experiments, and that's often a criticism of our work. However, those very high concentrations are being seen already today, and that's what I'm going to show you through this talk. So this is in what we call the Western Arctic. So this is the Pacific sector. A paper by Shadwick in Nature Climate Change, showing a progression of the Chinese icebreaker goes a pretty similar path, further and further towards the North Pole each year because there's less ice. They have created this time series. We start off in the top left, and then the top right. But what you can see, without going into too much detail, that blue area is where aragonite saturation is less than 1. So this is already corrosive water to pteropods and other pelagic calcifiers. But you see, very massive. And this is only a 2D version. It's not just going down as well, it's spreading out. So the area and the volume of corrosive undersaturated water is increasing here. There was a further study which tried to understand what was the main reason behind this change. And they identified that it was because of ice loss and it was because of freshwater release, but also that freshwater release was significantly changing the alkalinity or the buffer, basically the buffer capacity of the water. Therefore, any CO2 uptake was having a much greater effect on the pH or the aragonite saturation state. And you see in the bottom left here, again, this difference between corrosive water below 1 and that we've gone already from 98 and then through the 2000s, it's almost always corrosive water that they were studying, that they were showing. But it's not just in the Pacific. And I must admit, there was one thing I forgot in my first slide about what is driving acidification in the Arctic. A lot of the signals are coming from outside the Arctic. The Sheedy paper is showing that's actually mostly a result of strengthening of Pacific water. And we saw a talk earlier about the pulsing, these salt bombs, but they're also bringing in their anthropogenic carbon bombs as well. But we're also seeing big changes in the Eurasian basin or the Atlantic side. And this is work from the Swedish group from Ulfbo et al. And again, you see with time from 96 to 2017 that we're seeing, in this case, this is pH, but you see the pH is getting lower and lower and getting quickly lower. That's not English, is it? Rapidly lower. I've been in Norway for too long. Again, when we start looking also a little bit more locally or regionally in the Canadian Arctic, I didn't have the pictures of the corroding pteropods because I thought you were going to show them, but they also have empirical evidence, not experimental evidence, that this rapidly acidifying region, and these are the depth levels of these pteropods, that samples taken, pteropod samples from these. I can't. That doesn't work, does it? Sorry. Yeah. Oh, but isn't everybody watching me? If I just shout. The blue regions are undersaturated to aragonite. If you compare the shell structure, integrity, they are already corroding. And they move in looking for food, they move out to get away from predators, and then they start dissolving. So this is a high CO2 world happening today, or whenever they were sampling, but it's very likely to be still around now. This was in the AMAP report, but I just want to show another thing. I talked about this land-ocean connectivity, and it's in the East Siberian Sea where we get this incredibly tight connection from the Obs and the Yenisei rivers and others there, which are pumping in organic carbon. This is causing regions which are way below worst case scenario from IPCC models. This is very regionally, and this also supports this is a region that that Nadja was also showing is a real hotspot. We can, again, but we can see it happening now. It's a little bit difficult because to compare directly with acidification experiments and organisms, because this is also a region of significant darkening. The light is very, very low here because of the organic carbon. So this is like a multi-stressor effect. As this encroaches into other systems, or encroaches outwards. It's an experiment where you've got warming, you've got freshening, you've got ocean darkening, and you've got acidification. And you're a non-adapted phytoplankton trying to understand how to survive in this terribly inclement environment. And I only got this morning. This is in progress in oceanography. It's advertised in progress in oceanography. They won't actually let you get to the PDF yet, but it will be coming very soon. And luckily, the next speaker, Agneta, sent me this morning. This is hot off the press, and this is in the Fram Strait, a region where, and it's also in the West Spitsbergen Current, not in the Arctic East Greenland Current. Normally people are thinking of Atlantification and thinking, oh, it's going to be good for the Arctic. The pH changes are going to be lower. But they have observed waters you see at 35 salinity, which is Atlantic water, with aragonite saturations down to 1. And there's one thing that hasn't been talked about here, is that 1 is the geochemical boundary. That's as was said, this is where calcium carbonate dissolves. Organisms start feeling it at 1.5, 1.7. We don't have to get down to this number we've been talking about. Anything around 1.5 is a struggle for pteropods. It's a struggle for many species. And interestingly, and what they have done is broken down the interannual variability and related the aragonite saturation state that they've reported into primary productivity was unusually high that year, so there was a slightly higher aragonite saturation state. There was very big mixing in 2017. So we're really getting understanding of what is driving. And this is the sort of information which is really, really useful when we're doing regional models, when we're using the information from system models and focusing down on regions, and also reaching out to the communities that were talked about in the last species. We have to understand, where are those walruses grazing? What is driving that acidification rate? And it's this sort of approach which is going to be really useful for informing the models. So in summary, ocean acidification is already one of the most important stresses on Arctic systems. It's highly sensitive to emissions and to climate change feedbacks, like increasing land-ocean connectivity. And as I said and pointed out in the State of the Arctic Cryosphere report, which is advertised here, and you can get it off the ICC website, that above 450 ppm, which at current emissions is about 14 years, many parts of the current polar marine ecosystem will be significantly challenged, and many of those species will be driven into local extinction. And also in that report, you will see that it's shown that the recovery from these incremental changes that we're making, even if it's 1.5 degrees C that we hold to, the pH changes will last for 50 to 70,000 years before we get back to the system. So if we mess it up, you can't go and drag the CO2 out of the water. We've got to live with it. So stick below 1.5, please. And last one, but there's lots of information that you can get off the AMAT website of our last report as well, which can supplement what I've just said.
All right. Thank you, Richard. 14 years is not very long. So we need to up the ambition here. Remember, if you want to contact us and ask questions, are we getting any questions? Oh, yes. Yes, they're coming in. So if you want to get yours in, hashtag COP26 polar _OA. That's how you're going to grab our attention, and we're going to be able to ask your questions to our panelists live. So we have 2 more speakers. Our next speaker is Dr. Elizabeth Shadwick, who is based at CSIRO in Australia. She has worked on carbon chemistry and OA, ocean acidification, across many environments, from the North Atlantic to the Arctic to the Southern Ocean. She leads the Southern Ocean Time Series and the Australian Antarctic Program Partnership Biogeochemistry Project.
Good afternoon. My name is Elizabeth Shadwick. I'm a senior research scientist at CSIRO and the Australian Antarctic Program Partnership. The Southern Ocean plays an important role in regulating the global climate. It has absorbed the majority of excess heat and a significant portion of anthropogenic CO2. This service, of course, comes at a cost, and today I will talk to you about Southern Ocean acidification. It's probably not a surprise to anyone in this audience that the world has a carbon problem. This problem is both urgent and quantifiable. In the year 2016, the atmospheric CO2 concentration at the South Pole was greater than 400 parts per million for the first time in 4 million years. And just last month, observations at the Cape Grim station in Tasmania indicate the Southern Hemisphere concentration is now 413 ppm and continuing to increase. The ocean is tracking the atmosphere, and it absorbs about a third of our total emissions. These observations are from Hawaii, but the story is the same across the globe. As the atmospheric CO2, shown here in red, increases, CO2 at the surface of the ocean, shown in green, increases as well. The reaction between CO2 and seawater results in a decrease in pH, which is shown here in blue, and this is ocean acidification. However, changing ocean chemistry is not restricted to pH. As the pH declines, so does the saturation state, which is represented here by the symbol omega. This is a chemical threshold for the mineral calcium carbonate, which many marine organisms, from phytoplankton to coral to shellfish, use to make their shells and skeletons. If omega is less than 1 or below 1, it becomes more energetically costly for them to build calcium carbonate, and some organisms may even experience dissolution of their shells. Should point out that the Southern Ocean has naturally low saturation state. You can see that here with the pre-industrial distribution of omega at the surface. Organisms living in the Southern Ocean are therefore already close to this threshold. If we look below the surface, here a transect from Australia on the right-hand side to Antarctica on the left, the red line is saturation state equal to 1. So you can see that in some areas that's below a depth of 1,000 meters. In some places, it's above a depth of 500 meters. But as pH declines, this red line is moving closer to the surface. In other words, the areas of the Southern Ocean with supersaturated conditions are shrinking. This matters for calcifying organisms like this coccolithophore, this pteropod, who are already experiencing undersaturation for at least part of the year. Studies have also shown that early life stages of Antarctic krill may be impacted by high CO2 and low pH. These organisms form the basis of the entire Antarctic food web, and they're critical sources of energy or food for fish, seabirds, and mammals. I would like to emphasize that widespread undersaturation throughout the year in the upper layers of the Southern Ocean can still be avoided if we limit warming to 1.5 degrees and stay below 450 ppm in the atmosphere. But the time frame for that at the current levels of emission is 2030, so really less than 10 years away. The Southern Ocean is already changing. Acidification is not occurring in isolation. It's occurring in addition to both warming and freshening. This has impacts for the physical system, including ocean circulation and interaction with the Antarctic ice shelves, and also positive feedbacks for acidification because pH will decrease as the water gets warmer and fresher. The figure on the left shows the Antarctic sea ice extent. The red line is the 2021 season, which is now the third lowest on record and may yet surpass the previous 2016 anomaly shown in dark blue. The map in the center are the sea ice concentration anomalies, and we see that the areas in red, where the sea ice is significantly less than the long-term mean, are much more prevalent than the areas in blue, where there's actually more ice. Sea ice is a critical habitat for phytoplankton and krill, and also it's used by seals and birds for feeding and reproduction. We are monitoring Southern Ocean change through major domestic and international networks like the Global Ocean Observing System, the Southern Ocean Observing System, and the Global Ocean Acidification Network. This map shows the tracks of ships that collect surface water CO2 observations that are used to quantify the size and variability of the Southern Ocean CO2 sink. However, these observations are restricted to the surface waters and are heavily biased to the summer season when the region is free of ice. In recent years, technological advancements have really changed the way we can observe the ocean. Biogeochemical Argo floats, this little yellow guy shown here, carry both pH and oxygen sensors. So the floats sink to a depth of 1,000 meters, and every 10 days they rise to the surface collecting observations. These are then transmitted by satellite, and the float sinks back down to repeat this mission. They're able to collect data through the winter season, which has not been possible with ships. And so to illustrate the difference that these floats have made, consider this red line here. So this is a section through the Pacific Ocean that would be reoccupied by ship every 5 to 10 years and take anywhere from 4 to 6 weeks at sea to collect and analyze water samples to produce this beautiful section of pH through the ocean with depth here. The horizontal sections are the data that were acquired by 3 floats deployed from this ship and show all the data they were able to collect between April and the following January. Over the last 7 years, we have been able to collect more than 8,000 profiles of pH with this network of floats. Over the same period, only 1,000 profiles were made by ship. And so this shows in blue the floats that are active, and in red the floats that are either inactive because they've reached the end of their life or because they're currently under the sea ice. Other platforms like Saildrone, which is shown here, which completed the first autonomous circumnavigation of the Southern Ocean, so going all the way around in about 200 days, are also emerging with capability to measure CO2, temperature, and salinity, and really building on our observational records. I would like to emphasize that to track the progress of acidification in the Southern Ocean and to understand variability and extreme conditions, we need observations sustained over many years. And to do this in this remote region, it really requires global collaboration. The Southern Ocean is already changing, so I would just like to close by pointing out that the acidification that it has already experienced won't be reversed for many hundreds of years, even under the most ambitious emission reduction strategy. However, year-round, widespread calcium carbonate undersaturation can still be avoided with global commitments and global action. Thank you.
Thank you, Elizabeth. Excellent presentation. And now for our last presenter, Dr. Agneta Fransson is a senior research scientist and chemical oceanographer at the Norwegian Polar Institute and has more than 20 years of experience in polar ocean research. And she is also now co-lead of the newly formed Arctic Regional Hub of the Global Ocean Acidification Observing Network. Take it away.
I'm Agneta Fransson, Senior Scientist at the Norwegian Polar Institute in Norway. I will talk about the GOA-ON Arctic Hub and the indigenous and Arctic communities. And GOA-ON Arctic Hub is an international observing network for ocean acidification. And since there are few observations in the Arctic with large data gaps. And the Arctic Hub Science Steering Committee consists of it's myself, and it's also Dr. Melissa Kerici, Institute of Marine Research, Norway, Dr. Kumiko Asetsu-Scott, Fisheries and Oceans in Canada, and Dr. Jessica Cross at NOAA, USA. And here to the left, you see the map of the Arctic, and there is the polar circle, as you can see, but it is also the red area, or the red line from the ARMAC definition of the Arctic. And that is the area which is covered by the Arctic Hub. And it covers both sea ice and land, and there are large regional differences in the area with shallow and deep seas, sea ice, rivers, and glaciers. And there are Arctic communities living there in this area, and they are directly affected of the changes in the Arctic with the sea ice loss and thinning and increased ice melt, which you have heard about in previous talks. And this increased meltwater with river runoff and freshening has been observed during the last decades. And the figure here, you see the Eurasian river discharge in red, and also in the blue is a North American river discharge. It's slightly increasing, and this freshening of the Arctic with the ice melt and river runoff caused this decrease and dilution of carbonate ions and increased ocean acidification. And when you have less of these carbonates, then you will also have decrease in calcification potential for shell formation for some organisms that has calcium carbonate shells. And you see the photo of the theropod Limacina helicina, which has an aragonite shell, which is vulnerable to ocean acidification. And also with increased meltwater, you will also have increased ocean CO2 uptake, which will further increase ocean acidification. Warmer Arctic will lead to increased permafrost melt and organic carbon from rivers, and that may speed up the production of CO2 from carbon reservoirs on the shallow shells and also from the rivers. And you see on the figure here the map of the Arctic from Charette et al., the transpolar drift with fresher water transported from the Siberian shallow shells and rivers, crossing the pole over to the other side and out of the Arctic. And the more yellow is the fresher water, and that is also, you can see on the left-hand side, the organic carbon. In red, we have the high concentrations of organic carbon and also CO2. The observed chemical change of anthropogenic CO2 in the Arctic with the accumulation and spreading of this corrosive water with the potential of high dissolution of shells. From the figure here by Ulsbo et al., you see the Amundsen and Nansen Basin in the central Arctic Ocean with change from year 2005 with anthropogenic CO2 in orange yellow in the Amundsen Basin. It's increasing towards year 2011 with more orange color. You see a larger amount of anthropogenic CO2 in both Amundsen Basin and the Nansen Basin. And in year 2015, it has spread to the even more or accumulated in both basins and also deeper down to 1200 meters in the Amundsen Basin. And in year 2021, we will also have new data from recent Arctic Ocean cruises, such as the Nansen Legacy and Oden cruises, that also may give new answers on the anthropogenic CO2 and how it will evolve in the Arctic. So the goals of the Arctic Hub is to understand temporal and spatial variability of ocean acidification and their unique controlling mechanisms in the Arctic, and also to increase observation in collaboration with international group of scientists such as the Synoptic Arctic Survey, SAS, and Distributed Biological Observatory, DBO, as well as with local communities. And we will use new technologies and also developed for or adapted for Arctic conditions to get more data. Also to investigate responses of organisms and ecosystems. And an important goal is to communicate to local communities and policymakers to help developing mitigation and adaptation strategies by providing various future scenarios, for example, with modeling. And the international collaboration I previously mentioned is the Synoptic Arctic Survey. And here you see the map to the left-hand side, which is the plan for the cruises, where several countries are involved, such as Canada, Japan, Korea, USA, China, Russia, Norway, Sweden, and other countries. And to the right-hand side, you see actually the result from 2020 to 2021, where you have the cruise track in blue and the photos of the different icebreakers or research vessel and different countries that were involved in this survey, this Pan-Arctic survey for a comprehensive data set for the whole Arctic. so covers different regions where different variability and conditions. And I was on board myself this summer on the Norwegian icebreaker Kronplussåkon, and that was with the Nansen Legacy project. And I was cruise lead together with Bodil Blom, see on the photo here. And we crossed the deep Amundsen and Nansen Basin, and we also partly covered the northern or the shallow northern parts of the Barents Sea. The Arctic Hub, as a main goal, is the involvement and awareness of indigenous and Arctic communities. And we have an activity which we call Go On in a Box. And that is a small kit that we can provide to the communities around the Arctic, where they can take water samples and they can, with a more simple method, measure the water with regard to pH, alkalinity, salinity, and temperature. So this is something we want to engage all or different communities, so they get involved with sampling and also the analysis, and they can contribute to the data and science in Arctic. And they will also observe and be aware of the climate change. We also have an initiative called Shell Day, which is also similar activity where the communities or people go out one day and collect shells and also water, and they analyze them. So that's also one of our main goals, to involve as many people as possible in the Arctic communities to get this pan-Arctic data and involvement. And summary and take-home message, continuation and expansion of international and cross-interdisciplinary pan-Arctic observations are important for the knowledge of effects and chemical biological processes and ecosystem. And the involvement of the Arctic and indigenous communities is valuable and important for the increased awareness on climate, chemical, and ecosystem changes in the Arctic, because people live there, they will be the first one to observe the changes. And I also want to thanks for the attention, and if you have any questions, you can contact me on the email here.
Hi, everybody. Apparently, we're quite pressed for time, but because we want to listen to our Twitter audience, and we want to bring our panelists up if possible, we have at least one question coming from the Twitter audience, and we're hoping all of our panelists, someone may be able to jump in and answer. So, Sean, what is the question?
Am I on? Yep, I'm on. Great. So the first question that's come in over Twitter is there any contribution to ocean acidification from methane, and are the two connected, or are we not talking about the same thing at all?
Who would like to take that? Elizabeth, maybe?
Sure, I can have a stab at it. I would say that they are definitely connected, especially since methane is a stronger greenhouse gas in terms of its warming potential than CO2, about 20 times stronger. And there are processes that both produce and use methane in the ocean, but it does not cause the pH change the way that the reaction between CO2 and seawater does. Sorry about the echo.
Maybe one more. Okay. No, looks like, nope. We're getting cut off. I'm so sorry, panelists, that we're not going to be able to keep you up longer. We have to end the event, but thank you so much. The presentations were amazing, and thank you again.